Okay, so I wanted to have another go at introducing these notions of Frechet spaces. So I thought it best to start with an example. Here's a Frechet V-space. It has a set A, and each element of A in this case is just the numbers 1 and 2, there they are in our diagram, and each of these is associated with a collection of neighbourhoods. Now what a neighbourhood is just a subset of our set. And the collection of neighbourhoods associated with 1 is denoted zeta 1, and it consists of the set containing 1 and the set containing 1 and 2. These are represented by these black circles here. Now also element 2 is associated with a collection of neighbourhoods. In this case it just has one neighbourhood. So in this diagram I've used solid lines to denote the neighbourhoods of point 1, and I've used dotted lines to denote the neighbourhoods of point 2. So try to think about how this generalizes, because basically Frechet spaces is this basic idea. We have a load of elements, each element has a collection of neighborhoods. That's pretty much all there is to it. But these are very interesting spaces in the way that they relate to things in topology. And I also think it's probably the most intuitive route towards understanding some of the most interesting aspects of point set topology that I've found, to begin by studying these Frechet V spaces. So how are these things defined? Well, a Frechet V space, we can call it S. We can think of it as a pair. One of the things in the pair is the set of elements. We can think of this as a set of points. Perhaps sometimes I should refer to them as vertices or elements. It's some set. We'll typically think about a finite set today. And the other thing is that each element, x, so I've made a mistake here, let me just correct it. Okay, so this is an important piece of notation that I sometimes keep forgetting. So anyway, what I'm saying here is that for each element x of A, there is a collection of neighbourhoods of x. Now what is that collection of neighbourhoods of x? Well, what is a neighbourhood of x? It's a subset of A. And so this being a collection of subsets of A, it is a subset of the collection of subsets of A. So our collection of neighbourhoods can be viewed as a set of subsets of A. Each one of those subsets is a neighbourhood. And this is pretty much all we do so far to define the Frechet V space. So it's really just this kind of idea of associating points with collections of neighbourhoods. Now, of course, we'd want to imbue more structure into these sort of neighbourhoods if we want to start to abstractly represent particular objects. For example, a very nice idea would be that each point should be contained within each of its neighbourhoods. And we can apply restrictions like that as we will, and by applying sufficient restrictions we can get to the already very general notion of topological spaces, which are a specific type of Frechet V space. Anyway, so let's go at this again, okay? Just to make sure we understand what a Frechet V space is. We have a set A. Every element x of A is associated with one of these objects, zeta x of A. Zeta x of A is a collection of neighbourhoods of A. So let's just examine what these neighbourhoods are. Well, firstly, these neighbourhoods, sorry, I said neighbourhoods of A, I should have said neighbourhoods of X. These neighbourhoods of X, they are members of this set zeta x, because zeta x is a collection of all neighbourhoods of X. But what exactly is a neighbourhood? Well, it's just a subset Y of A. Okay? So let's just totally now, I know I've gone through all of this sort of algebra and it's quite difficult to follow sometimes. I probably should have started with this statement here, but I'll give it now in plain English what a Frechet V space is. It's just a set where every member of a set is attributed with a set of neighbourhoods, and the neighbourhoods can be any subsets of A. So it's a set A associated with the elements of which are associated with neighbourhoods. Those neighbourhoods are subsets of A, and sometimes I call this thing K instead of A, but it's this all-important sort of set of all elements of which comprises the sort of bits and pieces of which the neighbourhood structure we focus upon gives us our topological spaces. So yes, there we are. So what I wanted to do next was to try to illustrate how Frechet V-spaces may relate to other sorts of spaces you might know about, like topological spaces, or specific types of topological spaces, metric spaces, which include all sorts of very familiar things like the Euclidean plane and so forth. Now, in a Frechet V-space, we have this idea of a limit point. And it's this real notion of a limit point which allows us to connect, I would say, at least in my mind, from here to here to here, or at least from here to here. Because it's really by defining the idea of a limit point that we get very close to being able to attribute geometric structure to Frechet V-spaces. And so in my mind, this is the sort of path to understanding these Frechet the easiest path I found to understanding these Frechet V-spaces in a wider context is to understand this notion of what a limit point is. So I shall define that. Okay then, so this limit point concept, I would say, is a sort of linchpin to understanding the connections between these different kinds of spaces in a sense. So what is the definition of a limit point? Well, let's say we have a Frechet V space upon a set A. So it has a set A, and then I always make this. Okay, excuse me, I seem to have something of a real mental block about this. Anyway, yes, it's just a notational matter on defining what a Frechet V space is. It's still basically what I was saying before, every element is associated with a collection of neighbourhoods. It was just, I kept writing it in a funny way for some reason. Anyway, the point is a Frechet V space has a set A, and the other component of it is a collection of neighbourhoods, zeta x, which is of course a subset of the collection of subsets of A. But what I kept missing out of a notation for some odd reason was that, of course, there's one of these collections of subsets for every element of A. Therefore, I ought to have sort of indexed this set by noticing that there is one of these collections for each. So I should have put this such that X belongs to A part on the end of the set thing. Anyway, notational silliness aside, that's basically what a Frechet V space is. So, definition of limit point. If we have a subset E of A, and we have a point P of A, then we say that P is a limit point, also sometimes called a limit element, of E if each neighbourhood of P contains a point of E other than P. Think about it. Every neighbourhood of this point P is touching E somewhere other than itself. That's what a limit point is. Algebraically, we could say that for every subset E of A and for every point P of A, we have the property that P is a limit point of A when there's a neighbourhood of P. Sorry, when every single neighbourhood of P has a non-empty intersection with the set E minus P. That's a fancy way of saying that here's a neighbourhood N which is intersecting with E at a point other than P. Okay? And this is a very, very useful concept, as we shall see. And so sometimes we might write E dash to denote the set of limit points of a set E. So limit points are awesome. Just to give you a little taster of how awesome they are, a closed set. So if you know a bit about point set topology, you'll understand that the notion of a closed set is very important. you pretty much build up the theory from a theory of closed sets. Well, a closed set is just, in this theory, a set which contains all its own limit points. A subset of a space which contains its own limit points. So there you go. It's a pretty powerful concept. Anyway, I know that's all been a little bit abstract, so let's get down to a picture just to make sure we get a sort of intuitive sense of what a limit point might be, sort of in a picture. So here's our picture. We have a set of what, 1, 2, 3, 4, 5, 6 points. That we'll call that set A. Here's a subset E of these points. It consists of these three here. And then we have this extra point P, and we ask, is P a limit point of this subset E of A? So is P a limit point of E? And of course the criteria we need to check is that, is it true that every neighbourhood, and these neighbourhoods of P I've drawn as dotted kind of loops, is it true that each neighbourhood of P holds a point of E other than P? Well, let's check. Look at this neighbourhood. Does this neighbourhood of P hold a point of E other than P? Yes, it does. The same is true of this neighbourhood. So in this case, yes, this point P is a limit point of E. But you can think of lots and lots of cases, because of course there's lots of ways to allocate neighbourhoods to things, and this is the beauty of the Frechet space setup. But anyway, you can think of, for example, the sequence 1/1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Zero's not, if you think about it as a set of integers, the full sequence, sorry, a set of numbers, the full sequence, well, zero's not a member of it, but it's a limit point of it in the sense of a Euclidean topology. And all of these kind of ideas are kind of correspondent in a sense, here seeing them in a very pure form. And especially this notion of limit points, we see, because of the crucial role it plays in the definition of continuity, it really sort of pins things together. I mean, if you ask me what a sort of, I would just say, if you force me into a sort of non-topological definition of a limit point of a subset E, I would say it's a point which is either sort of inside E in a very sort of properly embedded way, or it is a point which is sort of arbitrarily close to E. Okay then, so now I want to explain the idea of continuous mappings. So I think it's good if we follow this sort of idea of this last diagram, and we're going to look at another diagrammatic description of this, and then I'll go through it algebraically, and I think this is probably the right way around to do it. So here we have a Frechet V space, and it could be any Frechet V space on any set or whatever. And here we have another Frechet V space. It's on a different set, maybe it could be different in all sorts of ways. But what is a Frechet V space? Basically, it is a set, and that's fine. We can do a mapping from a set to a set. We're thinking about transforming between Frechet spaces here via this mapping F. So it's fine to be able to map from the set that space S1 works on to the set that space S2 works on. What else is there in these spaces, in their structures? There is their neighbourhood structures, and aspects of their neighbourhood structures are reflected within their limit points. What are their limit points? We've already been talking about how limit points of subsets is this really kind of integral part of the topology, of a sort of topological aspect of one of these spaces. And so what we're basically just going to do is be very simplistic about it, and we're going to say, let's suppose we've got one Frechet V space, and it has all these subset. It's a set of something, set of cows, set of numbers less than 10, whatever, and it has all these subsets and it has all these limit points, and then we're going to suppose that we have a mapping from this Frechet V space to another Frechet V space. What does that mean? It just means mapping the elements that S1 is based on to elements that S2 is based on. And that's all well and good, but what's very interesting is if you can sort of have some notion of continuity. I mean, like the notion of P being a limit point of X is in some sense like saying that P is close to this subset X. Well, if F was a continuous mapping, maybe it would preserve something like that quality. So we use this as a sort of a reason to inspire us to define continuity in this sense, as saying that a map like this from Frechet space S1 to Frechet space S2 is going to be continuous when it has the property that whenever P, for any subset X of S1 and for any point P of X of S1, if P is a limit point of X, then F of P should be a limit point of F of X. So it's this notion of preserving sort of limit points of subsets, which we take as a sort of definition of continuity in topology, in this kind of abstract notion of mappings. And we can do this more algebraically. So here's a sort of more algebraic definition. So we've got a mapping F from a Frechet V space S1 to a Frechet V space S2. So let's write these things down, okay? They might be based on different sets. Maybe Frechet space S1 is based on set S1. Its elements will have different neighborhood structures. Once again, I forgot to index the x's, whoops. And similarly, we have this Frechet space S2, and its elements also have these neighborhood collections, which could be different. So, okay, we have a mapping, let's say, that sends S1 to S2. When would we say that was continuous? Well, here's our definition. The requirement of continuity is that if P is a limit point of a subset X in the first space, then F of P is a limit point of F of X in the second space. That's our definition of what continuity is. And so basically, what does it mean for a mapping from one Frechet V space S1, S1 to another space S2? Basically, it means that the limit points of subsets of S1 are consistently mapped to limit points of the appropriate subsets of S2. Okay, and here's one really cool reason why it matters to me. Homeomorphisms. A homeomorphism is a mapping from one Frechet V space S1, let's say it maps Frechet V space S1 to Frechet V space S2, and it is continuous, and it works as a bijection on the collections of on the sort of sets that these two spaces are based on. So it's a one-to-one mapping from A1 onto A2, one-to-one correspondence between the sort of elements of these sets. And as I say, it's continuous, and it also has a property that its inverse is continuous. Now, if F is a mapping from S1 to S2 with those properties, it's a bijection, that is continuous, that its inverse is continuous, then it is a homeomorphism. And homeomorphisms are wonderful things because they preserve limit points, and they essentially preserve all aspects of the sort of topological structures of things. In a sense, they're sort of like the sort of isomorphisms of they're sort of akin to the isomorphisms of graph theory or the linear transforms of geometry. They're things that you can do which don't ultimately affect the nature of the objects. They're sort of invariant transforms, and one might even say that the sort of goal of topology is to discover aspects of shapes and things which are invariant under these homeomorphisms, these sort of topological invariants. For example, a coffee cup in some sense is homeomorphic to a donut. You've probably heard this idea before. If I have some blue tack, perhaps I could show you, in fact, if I have time. Give me a second. Okay, so let's make a coffee cup. Alright, pretty shoddy coffee cup, but you can see that you can fairly easily sort of push out this bulge and continuously deform it into a donut. You see, the thing that you've done here though, you haven't affected any of the sort of limit points and the closeness properties as you've morphed this thing. So this is essentially a homeomorphism actually. So that's why one might jokingly say that a topologist couldn't tell the difference between a coffee cup and a donut, because essentially when these things are homeomorphic, it means they have the same kind of topological properties. But this gives us a wonderful way to organise topological spaces, and we can have like a single idea of a sphere that also represents cubes and and tetrahedra and all kinds of shapes, because topologically, you know, the sphere itself has all the necessary things that we need to study about that thing. So I love this idea of topology, just getting into it, but I think it seems really fun.